So it turns out that combinations have more uses than just counting outcomes or counting the number of subsets you get from a set of larger elements. Or larger number of elements. So we have this thing here called the binomial theorem, which is useful for expanding a binomial that's raised to a power. So you notice that this notation right here is new though. So off to the side here, I've defined it. And it turns out that nj, and the way we pronounce it is n choose j. Notice there's no fraction between n and j, so it's not a fraction. So this is all equal to c of nj. So this is another way of representing a combination, and we call it a binomial coefficient, okay? And it is used, like I said, to expand binomials raised to power. So let's look at a couple examples illustrated here. So if we have x plus y raised to the fourth, this is where I am right here. So we just basically follow the sum. Now the way that the sum is written, notice the inside of the sum. It's written so that the higher powers of x are written first, which is what we're used to, and then the powers of y are increasing instead of decreasing. So for x plus y to the fourth, we're starting with x to the fourth and ending up with y to the fourth, as you can see. And we just go through. The only tedious thing about this is calculating all of the binomial coefficients, but as you do more and more, you really get really good at this. You can figure out what they are. Now looking ahead at 2x minus 3y raised to the fifth, notice that that's the same as saying 2x plus a negative 3y raised to the fifth. So all of this is the expansion. So this is getting a little tedious. And then after you just compute all the numbers, for example, looking at this one right here, 5 choose 2 is 10. You have 2x to the third, which means 2 to the third times x to the third, and then you have negative 3y quantity squared, so that's negative 3 squared times y squared. If you multiply all of that out, you get the, x third, y squared. You get the 720 that's there. And so those are just the final answers for those two expansions. So feel free to pause the video and work them yourself if you like. I just thought you'd rather see it written down first than me just writing everything out step by step. But now looking at another example, let's say we have a binomial raised to the 25th. Can we figure out just one coefficient, x to the 12th, y to the 13th? And notice, of course, that those exponents do have to add up to 25. We're not going to get like a x to the 12th, y to the 15th out of nowhere. It has to add up to the power. So we know already that that term is going to correspond to this. And the question is, what binomial coefficient is going to go with that? Well, we know the binomial coefficient. We know the top number is 25. Oh, and here I go. I wrote 15 and I meant to write 13. I had 15 on the brain. There we go. So which number do we put in the bottom? And turns out, if you look back up at your binomial theorem, the bottom number, j, is the same as the power on y. So that's the one that matches up. Now, as we're going to learn in a little while, it's not going to matter. You could use the 12 or the 13 because of a little property of binomial coefficients. So what is this magical coefficient? I'm just going to pull that up here. It is, get ready for a huge number, it is 33959 763 545. And of course, I just use a calculator that can handle these big numbers. Chances are when you put this into your calculator, you'll get scientific notation. So that is in the, well, let's see, that's millions, billions, trillions. That's 33 quadrillion, almost 34 quadrillion. And that's because that coefficient is really, I didn't write that down. I'm going to keep this as 25 choose 13. This is 2 to the 12th and 3 to the 13th. And if you compute that all out, that is the coefficient that you get. So definitely a lot of x to the 12th, y to the 13th terms there. Okay, some corollaries that happen as a result of the binomial theorem. If I take the original x plus y to the n, and I substitute 1 for each of x and y, well, what's going to happen there? Well, that means that you're going to have all of this in the sum, and we know that 1 to any power is 1. So we end up with the sum, j going from 0 to n, of the binomial coefficients, and it's equal to 2 to the n. So that means if you take every possible binomial coefficient with n as the first number, they're all going to add up to 2 to the n. That's interesting. Another interesting piece is if we say x is 1 and y is negative 1, of course it works the same way if you let x equal negative 1, y equals 1. Well, what happens inside of the sum? Now we know that 1 plus negative 1 to the n is 0 to the n, which is 0. So if we're adding up all of these, well, this term is going to go away. I'm sorry, that's not 0, that's 1. And we're going to end up with this. And what that basically says is if I alternate the binomial coefficients, starting from 0 and ending up at n, they're going to add up to 0 if you alternate positive and negative. That's interesting too. And we're actually going to see why that is when we get to the binomial, or to the Pascal's triangle, in a moment. So stay tuned. Thanks for watching.